All right, so it's the last session of the day. Kind of. It was a closing plenary, so second to last session of the day. Well, we have a great session today on load flexibility, and I have an older name here. I think it's load flexibility and carbon accounting. And at first blush, we're kind of struggling with the name to try to make sure we can send the intent. But I think what you're going to hear about is various ways to save on scope 1 and scope 2 emissions. One on the electrical side, thinking about demand management, and then we're going to have speakers from CARB to talk about the scope 1 emissions. So I think collectively you're going to get a great scope 1, scope 2 emission abatement sort of talks. So to kick us off, we're going to start with Vedant Sinha from UC Davis. Vedant is a final year MS Energy Systems student at the UC Davis Energy Graduate Group. He recently finished a stint as a transport analyst at the International Energy Agency in Paris. Since starting his graduate degree, he has worked on load flexibility, clean power procurement, and carbon abatement economics as a graduate researcher, under Professor Kelly Kissick's Industrial Decarbonization Research Group. He received his BS with honors first class degree in political economy from King's College in London in 2022 and secured the first position at King's College London's Climate Policy Pitch 2022 for a scheme on funding carbon capture technologies in the UK's industrial clusters. And I'll pass it to Vedant for his, I'll cheat, I already know what his presentation is, it's gonna be great. So. You're up.
The question of renewable electrification in California is becoming more and more not just about where your power comes from, but also when you consume it, which is why I'm going to talk to you about industrial load flexibility in California, the challenges and opportunities to realize costs and carbon savings. I developed this study with the help of my professor and advisor, Professor Kelly Kissick. And to start off, this is my brief background and what led me to my interest in load flexibility, working on industry and transportation and realizing all the electrification we're doing, we need to have load flexibility built into that. Now, to introduce it, load flexibility, demand response, load management, there are multiple terms. It's basically involving either changing the timing of loads or reducing loads. So this is what a shift would look like, blue being the modified load. This is what a load shed would look like. Now, why load shift? The first reason is for grid balancing in California. We have the infamous duck curve trend. It gets deeper and deeper during the day during excess renewables. So the idea is to move excess demand from the evening hours of coal and gas peaker plants, high intensity, to the surplus renewable hours in the middle of the day. A balanced, stable grid can reliably provide electricity to its industrial customers. There are potential cost savings, predominantly from moving from on-peak high-cost hours to off-peak low-cost hours. We also can realize scope 2 emission savings when we consume more electricity during the middle of the day. And finally, it's essential to accommodate more load growth. Now, if you're an industrial facility looking to electrify and you want to install a heat pump, the utility and grid operators would find it challenging to do so if the grid cannot accommodate excess demand during your on-peak hours. In the background, we have policy targets enabling load flexibility. We have digitally optimized DERs that can respond to carbon and price signals and shift around flexible processes like pumping, pre-cooling, heating, refrigeration, even rescheduling shifts. And finally, we have a piece of a puzzle, which is the industrial time of rate schedule. There are two components: the usage charge that applies a dollar value to the kilowatt hours consumed in a period, and a demand charge applying a dollar value to the highest demand in a period. Typically, there being three periods: the on-peak being the most expensive, moving on to off-peak being the least expensive. That's the duck curve becoming the canyon curve, by the way. We need to change the name on that. For our methodology, we took a representative medium facility load profile from the PG&E P19 grade category, and then we modified it by simulating some load shifts, doing about 10% of flexible load. We then calculate monthly bill impacts using usage demand charges, and also scope 2 emission impacts using hourly emission factors from mineral cambium and other sources. So in scenario 1, we shifted about 50 kilowatts from the entirety of the on-peak period, 4 to 9, to the early morning and some middle of the day hours, 8 to 1, completely off-peak, on-peak. And in terms of impacts, we expected to save on usage and demand because on-peak's more expensive, moving to off-peak is the saving. But the demand cost impact was also contingent on whether your new added load raised your monthly maximum or the whole highest maximum for the month that is also billed on top of these periods. So here are the bill impacts. We see a total bill reduction of about 1%, mostly driven by usage cost savings, but some demand savings as well. But the question is, are larger savings possible? And does every combination of load from and to generate savings across the board? In terms of scope to emission impacts, we saw about 1.5% drop in emissions. And the question still remains whether larger CO2 emission savings are possible. Now, in scenario 2, we thought of a more constrained load shifting scenario where a facility cannot shift load from all the on-peak hours and can only shift it to some middle of the day hours. That's 50 kilowatts, same amount from 4 to 7 to 12 to 3 for the months of April and September. And here's where the problem emerges. The additional demand charge payments completely wipe out any usage cost savings, and your bill goes up by around 1%, your emissions fall by less than 1%. And to look into this, we zoomed into the month of June to see what's happening, just the month of June, the same scenario. So when you move away 50 kilowatts, let's say you cut it out from the on-peak periods, you generate demand savings there, but those savings are limited because you didn't cut the 50 off for the entirety of the on-peak period. And that's when you're billed for the next highest load in that 4 to 9 gap. So your effective savings are not in the first picture, as you can see, the 50 reduced there, but actually the 445 and the 417 that is billed as the next highest maximum. That your savings are limited, essentially. And then there are additional charges you incur when your part peak charge goes up and you have a new monthly high maximum demand. And this is what we observe in the month of June's bills as well. So we blow up the demand cost component. You do save on peak, but the savings are limited, and the monthly maximum and the part peak charges wipe out any savings you could get, and your bill rises. So the current TOU rate structure may not be optimal in all scenarios to shift loads. Now, here's where we depart from the TOU rate structure. We went beyond it, and we thought, what if we were not constrained by the periods it has, the demand charge structure, and instead we shifted all the load from late in the night and evening hours to the middle of the day without thinking of TOU periods. And we build it using what is called the CalFuse pricing method. So it works as follows. You have that red original load that is billed at the TOU rate structure, and any deviations from it are actually billed at an hourly rate. Your final bill comes out to be your original TOU bill plus or minus any savings you generate with the load flexibility you did right there. And so here are the bill impacts. It's more economical to shift load under a CalFuse pricing regime, about 4% cheaper than under TOU, and you also save compared to your original time of use bill. And it comes out as the more cost-effective method to load shift. The scenario is laid out up there, and because you're not constrained by TOU periods, you're shifting for all non-renewable hours to the middle of the day, excess renewable hours. Here's where we went even further. In scenario 4, we applied a dynamic hourly rate, an hourly rate to the whole blue load profile, and the same scenario as scenario 3. And here's where we see further savings. And even under a dynamic pricing regime, it is cheaper, around 2% to load shift versus to not load shift. And the TOU cases, it's not economically viable with the original load with no load shifting there. The bill is high. The bill further increases under a TOU rate structure if you modify that load doing the shift above. In terms of our scope to emission impacts, we saw emission savings that are 2 to 6 times higher compared to scenario 1 and 2 under TOU structures because you're not constrained by TOU periods. You can move completely from late in the evening and night to the middle of the day. And the emission savings in this case fell around 3% and 2 to 6 times higher. The conclusions we got were the fact that the current TOU rate structure creates limited opportunities for cost and carbon savings. Demand charges pose the greatest barrier to that, eventually limiting the cost and carbon savings potential. Alternatives to the current TOU rate structure, like the CalFuse pricing method, as well as the dynamic rate, have a higher potential of cost and carbon savings, and these alternative billing rate structures are not limited by demand charges, TOU periods, and could be a way forward depending on further questions of cost recovery for utilities, certainty for consumers, and other issues, but there are cost and carbon savings to be had. That's me. Thank you.
All right, thank you, Vedant. Clearly, electric tariffs are hard and complicated, and we need to be able to play with them and some flexibility to achieve these energy savings. And I left, Vedant, do you mind just grabbing me that folder? I left my introductions. So next we have Sam Murthy, who's a research scientist at LBNL. Specifically, she's an energy and environmental policy researcher at Lawrence Berkeley National Lab. Her research focuses primarily on understanding the importance of demand flexibility and modeling its impacts on regional power systems throughout the US. She has worked on improving bottom-up estimates of demand response potential in the residential and commercial sectors in California by leveraging the heterogeneity in load consumption patterns. She's currently working to develop representative load profiles in the industrial sector that could be used for similar analysis. And Sam has a master's degree from Carnegie Mellon University and is a first-year PhD student at UC Berkeley within their civil and environmental engineering program. Sam, the floor is yours.
Thank you very much, Prakash. I'm not yet a research scientist, but I hope to be one once I earn my PhD. Thank you very much for having me here. I really want to thank Energy and Efficiency Institute for giving me this opportunity. And today I want to talk about load flexibility in the industrial sector. I think Vedant gave a very good overview of tariffs and bill impacts in the industrial sector and covered some parts of what I wanted to talk about today. But I would probably add a couple more points to it. But I also want to talk about how important understanding load profiles are in figuring out how much load flexibility there is in the industrial sector, just because there's so much of variety and heterogeneity in the way industry consumes electricity and so much of heterogeneity in the way processes are operated. And so we need to sort of account for all of these nuances. So with that background, I just want to drive home two key takeaways from my presentation. And the first is today, we don't have a good set of granular data that can help us understand what the underlying load profiles are for the industrial sector across different subsectors, regions, climate regions, sizes, and so on. And it's very important for us to have this, especially as we look at understanding what load flexibility means. And in addition to that, there is also the challenge of understanding how these end-use loads are behaving over a period of time. So there are not a lot of granular data sets that can help us understand the different end uses across industrial sector and how that is distributed over a period of time. So developing these kinds of analysis and coming up with these kind of data sets can really help us inform really what the capability of industrial sector is in terms of load flexibility. And of course, as Vedant alluded to, electricity rate structures today are pretty archaic in terms of the demand charges. And so these can really hinder the ability for industrial sector to perform any sort of load flexibility. So I will be talking about two of my research projects at LBNL that touch upon these two areas. So in the first part, we tried to do some modeling to understand if we can come up with load profiles that can represent the industrial sector. And we have hourly metered data for over 20,000 industrial customers within California across various subsectors. And this was collected as a part of another study where we were looking at DR potential for all of California. And we decided to kind of take a look at this and see, okay, what are the different load profiles that represents the industrial sector? And so we subjected this whole data set to a k-means clustering algorithm, and that generated a bunch of prototypical load shapes that you can see as individual lines in this figure. We then went ahead to perform a little bit more qualitative analysis on these load profiles to understand, okay, when do the peaks occur? What is the width of each of these peaks? And then regrouped those prototypical load shapes into these 12 different categories that you see on the screen here. And this gives us a pretty good understanding of the different kinds of load shapes that can be expected across different subsectors in the industrial space. And we also assigned a name to each of these superclusters. We call these superclusters, and we assigned a name that makes sense. So for example, night narrow means that there is one peak that is occurring anytime in the night, and it has a narrow width. Or morning medium is a single peak occurring in the morning, and it is medium wide, and so on. Now we can look at how the distribution of these load profiles look like across these 20,000 customers that we had the data for. And from this, it's pretty evident right off the bat that small facilities exhibit a lot more variety in the way they consume electricity than larger facilities. About 90% of these ultra-large facilities have flat or flat-ish kind of load shapes, but smaller facilities have a lot more variety in it. We also took a look at what this distribution looks like across different subsectors within the industrial sector. So for example, the second column over there indicates the beer subsector, and you can see the pink color bar indicates that there is like a significant chunk of evening-wide load shapes, which you can think of as like a low-hanging fruit for demand flexibility, for example, or petroleum refinery, which is the third from the last here, which primarily has just flat load shape throughout the year. Okay, so we use these distributions to also try and simulate load profiles for industrial sector across the United States. And this work was done in conjunction with some of our colleagues at Oak Ridge National Lab. And we were able to develop individual industrial facility level load shapes using a combination of the data that was provided by them and our methodology and understanding of these load shapes. But even with this work that we have done so far, we're still barely scratching the surface. And there's so much more to understand. And we encountered so many gaps in our own work, and I wanted to highlight a few of those. And to get started, the first gap that's quite glaring out there is just the lack of metadata. So we heard a lot of speakers speak today, and even in the previous session, about doing facility level analysis, understanding it on a facility by facility basis. But when we as researchers kind of look at this from a regional perspective or from a national perspective, we don't really have data sets that that has the count of industrial facility just by the demand, by the size, by the region, and what subsectors they represent. And this can be like really valuable information that can help us understand the lay of the land in the industrial space. Further, I spoke briefly about this, the end-use load disaggregation. Today, for any sort of end-use load disaggregation, we refer to manufacturing end-use consumption survey, or MEX data. And MEX data just provides a single value for each of the industrial end uses, and that is not helpful, especially in the perspective of load flexibility, because we don't have an understanding of what the temporal variation looks like, for example, and that can be very valuable information. Also, the spatial resolution in that data is quite limited. So again, we cannot perform highly granular analysis to estimate load flexibility potential. Further, it is important to understand the heterogeneity in the way facilities operate. There are a lot of nuances to industrial processes, their operating schedules, and really understand any kind of constraint that could limit the way industries can perform load flexibility and be able to model those and account for in our analysis. And all of this is just going to help us get to the point of what load flexibility looks like today. In the future, when we're thinking about electrifying industrial end uses, we also need to understand not just in terms of the magnitude of the load that they are going to add to the grid, but also if they're going to change the shape of the load profiles and how it really impacts our ability to flex load. So that was one part of my talk. And the second one, I just want to give a very brief overview of industrial rate structures. But as I mentioned, I think Vedant did a very good job in doing that already. As he mentioned, obviously, the current rate structures are very archaic and misaligned with the grid needs. And that's mainly because of the demand charges. And there are two types of demand charges, non-coincident and coincident demand charges. While coincident demand charges might be useful in helping move load away from the peak hours, non-coincident demand charges don't do much, especially in the context of California when there's so much midday solar generation and industrial loads are the ones that are able to soak up all of that generation. If you start to penalize higher demands during this time of the day, it's going to hurt these kinds of customers. So in one of the studies that we did, we found that the demand charges for an average medium to large C&I customers is anywhere between 27 to 40% of their annual bills, and that's a significant portion of their annual bills, and that's a significant sort of hindrance to the way they can perform load flexibility. Of course, there are a lot of talks of making these rate structures more dynamic in nature, but it's going to depend upon what that end rate structure looks like, how dynamic it is, and what the components of that look like for us to really be able to understand the load flexibility potential. But yeah, that was what I wanted to tell you all. Thank you very much for having me. Yeah.
Sorry. Thank you very much. Okay, well, that was fantastic. Thank you, Sam. Okay, so now we've just discussed from Sam and Vedant this idea of load shifting. I think the undercurrent here is clearly being able to recognize that emissions change on an hourly basis, right? And being able to take advantage of that, modifying operations to lower emissions. Now, to me, and when there's enough barriers, I think a whole host of them, but to me, I think another barrier is why would a facility do it if they're not going to get credit for it, right? They don't want to move load to every hour and just feel good about themselves. They want to put in the corporate sustainability report. They want to be able to say this drives towards a target, which moves us to the next step of our session, carbon accounting. So we have two speakers who are going to talk about carbon accounting, starting with John McGrath, who's at Rocky Mountain Institute. John is the Technical Product Director for RMI's Climate Intelligence Program, which leverages data and technology to enhance climate performance across material and energy industries. Before joining RMI, John was a Sustainability Product Manager at Amazon Web Services. Prior to that, he was Chief Product Officer and co-founder of the HR technology company Intello, led product and software teams at Wordnik and the Woods Hole Oceanographic Institution, and was a software developer in the newsroom of the New York Times. John has a master's degree in journalism and new media from Columbia University and a bachelor's in history and environmental studies from Bowdoin College. John is going to talk to us about his work in carbon counting, and I'm very excited. Thank you, John. Let's please welcome him to the stage.
Thank you, Prakash. Sorry, I feel like it's my fault. The title of this got sort of munged at the last minute. Let's see. There I am. So the theory of change for a lot of the work being done by my team at RMI, which really our job is to build technology and software that's public-facing for different programs in the organization, but a lot of it lately has been supply chain related. Our theory of change is that in order to drive down Scope 3 emissions, which by various estimates are between 70 and 90+% of a given organization or company's emissions, we need emissions transparency at the product level. So to understand the embodied emissions and the things you're buying. So we see this as a need. Why would companies see it as a need? You know, you get a big who cares from many of them who will do, you know, there's a bunch of very good actors in this space, but probably a larger cohort of people who will do the least they need to at the lowest cost. We're at a critical juncture where there are a lot of forces aligning to make that no longer possible. Some of those are changes to voluntary carbon accounting standards like the Greenhouse Gas Protocol. Mounting regulatory pressure is probably the biggest hammer, and I'll speak a little bit about that. Corporate purchasing requirements, and all of those are requiring change in what had been a fairly slow-moving field. And it's also, so it's a pressure on companies, but also an opportunity because it allows for market differentiation and entry into markets where there otherwise might be barriers. So the Greenhouse Gas Protocol is rather long in the tooth. It's over 20 years old. It is being redrafted as we speak. That's a relatively slow process. It's been ongoing for at least a year, I think more. Next year, standards should come out, and that is going to trigger a widespread reevaluation of corporate accounting standards as companies and other organizations adapt to what's released. Concurrently, and right now, there are a number of national and subnational policy and regulatory changes happening that are requiring immediate change in order for businesses to be able to operate and to sell into, you know, like small places like Europe and California. There's also sort of sector-specific regulations about methane emission charges from the IRA. But if you look at things like CBAM, the cross-border adjustment mechanism, which has been phasing in over the past year or two in Europe and is gaining teeth right now, in order to sell products in high-emitting categories like steel and cement, vendors will have to understand at the product level the embedded emissions in them and report those to regulators and to the purchasers. The same is happening in California through SB 253. 53 is it? And this is a little bit of an outdated slide, put a little sad face next to the SEC. They were evaluating requiring Scope 3 emissions. That isn't something they're going to do now, but they put the fear of God into a lot of organizations that this is now something that if they're not having to do it immediately, that's going to resurface. So if we go through each of these, let's see. So that regulatory pressure, this is the biggie. This slide is like 80% of what's getting people's attention. But if you also want to sell into, you know, forget Europe and California, to Amazon, starting next year, they too are requiring emissions reporting from their suppliers. So the pressure is coming from multiple directions, and this is all resulting in a tipping point where in order to do business effectively, you have to have carbon accounting and specifically product level carbon accounting. It's no longer sort of a nation state level thing or sort of a nicety to bury in the back of your annual sustainability report. The only way to really do this effectively is with technology and software. I know this through painful experience because I was the person at AWS for a year where if you called and said, we need the carbon emissions of our cloud computing usage, I would try to get it for you. And really it was like 80% of my job for about a year was just being screamed at by the very largest customers we had because we had no automated systems to do this. We could do it, and it would necessitate like 10 emails back and forth between myself and eventually someone else and you know, these giant customers. Now they have a system built into their billing console where you can just go and get it yourself. I'd say it's not quite all that it needs to be, but now, like, it used to be 600 customers, 60,000, 600,000 people use this. And it's automated or close to it. All the other cloud vendors now have the same thing, and this is something that we're going to have to see in many more spaces. The kind of data that flows through these systems isn't very valuable if it can't be compared. So a big part of RMI's work is developing methodologies for high-intensive, for the carbon accounting in high-emitting sectors. My colleague Sravan is here, and he is doing a lot of this work in metals and aluminum to develop these, and petrochemicals is another field we're working in, to develop these methodologies. Those need to be paired with data formats to allow the results of the calculations that conform to the methodology to be exchanged. So buyers and sellers can receive this information automatically so that you're not on the phone yelling at some poor product manager, but instead you can configure your software system to talk to another software system. The companies don't even need to be aware that this is occurring. And you can exchange data in a way that both heterogeneous systems, which is important, can read it. And this allows scalability of this whole endeavor. Once you have everybody really absorbing the fact that as of right now, you're going to have challenges in Europe and California, we're anticipating significant growth in the carbon accounting software market. We're starting to see that. So this is, it's one of course, you should look at this as a challenge and an opportunity, because the people who are ahead of the curve in doing this, for one thing, can charge a green premium, and we see that. For another, just aren't going to get whacked on the side of the head by these legal requirements. The market size of the carbon management software sector is going to grow considerably by consensus. Exactly how much, hard to say. That is a bit of a fluffy category because carbon accounting features are increasingly being embedded into other softwares that run large enterprises. And in fact, some of the big vendors are primarily ERP or enterprise resource planning software vendors who are adding carbon capabilities to it. This sort of just to illustrate that I'm not the only one talking about this, or RMI isn't. There's a lot of attention being given to the fact that this is how we're going to use market pressure to drive down emissions in certain sectors. Some of these standards are being developed at RMI. Some are being developed at other bodies and partners of ours. WBCSD, the World Business Council on Sustainable Development, has developed a sort of a techno-economic framework called the Pathfinder framework. Under that umbrella, they have a technical standard for high-level exchange of product emissions data. It's sort of like at the, this product has this many emissions, it can apply to any product. That format, called the PACT format, can be extended for any given sector by third parties. So as part of the methodologies work that RMI is doing, we're pairing those methodologies with PACT format extensions for steel, aluminum, petrochemical, I think eventually cement, of course, in order to add the sort of technology oomph to the methodological rigor that we're advocating for. This is, you don't have to look at all these, but this to just indicate big companies are starting to take, not fast enough, but significant steps into doing this and enabling their customers to do it. And maybe most importantly, requiring their own vendors to do it. Because I think one of the big forcing functions is to say, we have to do this to get the data we need. Everybody we buy from has to do it as well, and you're going to get, sort of a cascading effect. So it's going too slowly. The drivers are real, and they're increasing pressure. Technology is needed to do it at the scale necessary and to drive down the costs of doing it. Like, this is a cost of doing business. And it's inevitable. So this was a hypothesis even like a year or two ago, and now you see it happening. So one of the goals of RMI is to basically grease the skids. Make this thing that we know is coming, let's make it easy. Like, the path of least resistance should be to adopt common methodologies and common data standards, and we're trying to encourage that. So, Thanks.
Thank you, John, for that. Do we have any students here in the room? You raise your hand. Some students. Anyone else catch a $23 billion market cap? I'm not sure what you're doing. Go get paid. Let's go. You know, there's a lot of money to be had. Well, and that was fantastic. I think, honestly, from the research community, I could say we developed tools, models, data sets, and we sometimes can forget, well, these need to be transferable and communicable to other people. And I think this is something that John's highlighting in spades, that how we communicate this information is key, which brings us to our next speaker, David Allgood at CARB. And as a little side story, David and I first met at the first symposium, and we've had an opportunity to work together since, and we wanted him to come and speak this time. So an example of the relationships we're trying to build today. David Allgood is a staff air pollution specialist for the California Air Resources Board. He has worked on the California Cap and Trade program for the last 15 years, focusing on leakage minimization through free allocation, industrial benchmarking, and decarbonization of the manufacturing sector. David has also worked closely with industrial facilities complying with the Cap and Trade program and has visited nearly 30 different sites in California, from mining to food. David earned a master's degree in mechanical engineering and a bachelor's degree in physics from UC Irvine. David, the floor is yours.
Good afternoon, everybody. I'm David Allgood. I work for the California Air Resources Board. We are the regulator, or as John called us, we are the hammer. So you have to listen to me on this. So I'll be talking about our California Cap and Trade program, which is one of our major programs and policies that we're using to drive emissions in California down. So this slide just gives a overall of the very ambitious targets that we've set to reduce greenhouse gas emissions. The line graph on the left shows our annual statewide emissions since 2000 through our greenhouse gas inventory, which is published online as well. And then we have the targets for our 2020, 2030, and 2045 greenhouse gas targets. So in 2006, the governor of California set to law the 2020 target for 1990 levels, which was 431 million metric tons of CO2. In 2016, we set SB 32, and that set targets for 40% reduction from that point by 2030. So we have already met and surpassed our 2020 targets. We did that several years ahead of time. And now we're moving forward towards these really deep cuts in greenhouse gases from the state. And then in 2022, new legislation, the AB 1279, established two goals for 2045 for carbon neutrality. The first is to reduce anthropomorphic greenhouse gas emissions by 85%, and also to reach carbon neutrality, which means we're trying to reduce our emissions as much as possible, and we have to counterbalance that with carbon sinks, either through direct air capture, carbon sequestration, or through natural means. So this approach is to first prioritize emissions reductions where possible, and then to address the residual emissions through increasing natural and mechanical carbon sinks. And achieving carbon neutrality requires us to use every tool available to reduce greenhouse gas emissions and remove carbon dioxide from our atmosphere. To chart this pathway, the 2022 Scoping Plan update included a comprehensive analysis on the tools needed to reach these targets. This will involve deploying a broad portfolio of existing and emerging fossil fuel alternatives, clean technologies, and this is all to align with our statutes and our executive orders. And I really want to push all of you to read the Scoping Plan. It's the definitive document on how we plan on going from where we are now to some of those very tough targets that we're moving forward to. And then shown on the right is just an example of some of the charts from our Scoping Plan, which shows the energy demand of industrial manufacturing from now into our goal here of carbon neutrality in 2045. There's a massive shift in fossil gas to electricity, hydrogen, and other and bio-derived fuels. And also shown in this graph is that the energy consumption is going to go up. As we're going to these other alternatives, we're going to need more energy, more electricity to derive these fuels that we're going to need to use. And so it depends a lot on displacing these fossil fuel mixes with a mix of electrification, solar thermal, biomethane, hydrogen, and other low carbon fuels. And we've heard this from almost everyone, how heterogeneous the industrial sector is. And so these strategies employed depend greatly on the subsectors and the specific processes of each of the plants out there. So like our regulation, we need other policies that support decarbonization strategies, as well as a lot of the incentive programs. And I don't have a slide on this, but I'm really fascinated to see the short-term and long-term impacts of the billions of dollars that are coming through the federal government. Because I see those, the GFOs come up, and I'm really interested in the 5 and 10 years afterwards to see, how that's kind of changed the landscape and emissions in our industrial sector. So this slide talks about reducing our industrial emissions. Again, I'm focused on industry, so a lot of these slides are on industrial emissions. And you can see a lot of the technologies that are available or on the left, which include improving waste heat recovery, energy efficiency, fuel switching, electrification. And then recently there was a bill that requires CARB to look more into this carbon capture and sequestration. We are set to, we started a new group. We're set to perform a study on that to look greater into our CCUS, which is going to be a very useful piece as we move towards these really tough targets. And then also I had a colleague speak earlier on our embodied carbon work, and so that I fortunately didn't get to see it, but I know a bit about that program. And here's some of the good news that we've had. We've continued to show massive growth in California's economy and a decrease in our statewide greenhouse gas emissions. So, and even the industrial sector from 2000 to 2021 has decreased by 20% in emissions. And as the figure on the right shows, that California's emissions and economic growth have continued to decouple, meaning that we can grow our economy, and that doesn't necessarily mean more emissions out there. So we're off to an excellent start here, but I think these targets are going to be very stringent as we are moving forward, and so it's important that we work together with additional technologies, policies, incentive mechanisms to meet these long-term goals. And I added one more slide on here. There's been a lot of talk because a lot of the folks here have been in the building side and using a lot of cement. So we have a bill, SB 596, which requires CARB to develop a comprehensive cement strategy, a net zero cement strategy by 2045. So we're looking into greenhouse gas reduction technologies to evaluate these needs. That includes, much of the same that I've said before with fuel switching, electrification, CCUS, and changes in our cement mixes. So we're going to be putting together a report on that should be coming out in the next couple months to kind of lay out a scoping plan, if you will, specifically for our cement sector. And with that, I'd like to, I guess we can wrap it up and open it up to questions. Thank you very much.
All right, how about one more round of applause for David, John, Sam, and Vedant? Wonderful job. And we do have time for questions. I think our session is supposed to end at 3:15, and we have a good 5 minutes. So I'll open the floor to questions. You're not going to have a microphone runner, as you can tell I can't run, so I'm just going to have to speak up. Any questions? Yes. Maybe if you can stand up and maybe also say your name.
Jason Conrad, thank you. So I feel like some people are speaking to the idea of the United States creating regulatory standards. Are there standards that exist elsewhere in the world, perhaps in Europe, that could be adapted to the United States?
Are you talking like carbon accounting?
Yes, perfect.
There are. They cut both ways. Like there's what's it, the Global Battery Alliance has a standard called the Battery Passport, which eliminates the embedded carbon batteries and their components. PACT is actually led by a Swiss developer based in Germany. There's a lot of I live in the area and have a lot of calls at 6 in the morning because they're mostly the people in Europe. So there's a lot of cross chatter. And I should say, we strive to not create new standards. We find existing ones, put our shoulders behind them to avoid a tower battle.
For instance, a manufacturer of a steel product could send out all of their dirty products to, say, India and sell their clean ones to Europe, not really making any difference overall, and having an overall standard situation would really try and reduce that.
If all the different jurisdictions' perspective, then that's the good thing. Yeah, I think that'd be a problem for a long time.
So if you guys, there's a conversation here on carbon leakage and the idea that these universal standard could support or not support, stop leakage. Phrase. Thank you for that question. And any others? Yes, Kelly.
I have a question for John. So, John, when you were talking about product-specific embedded carbon, does that mean if I go on Amazon and buy a bicycle tire, someplace I'm going to be able to see the CO2 associated, embedded in that tire?
So I think Amazon in some cases will allow that, but it's sort of a top-down analysis typically. In the beautiful future, maybe you'll be able to roll everything up by saying, all right, my car has aluminum, steel, and glass in it. I asked those vendors, the people who bought the bumper from, asked their suppliers, and you just roll it up. I don't think that'll ever happen because there's a lot of disincentives, and you just need a few along the way of people saying, actually, we're bad. Our emissions characteristics are awful, so we're just going to not do it. And the whole thing collapses. So I have, these are early in the supply chain commodities really that we're first talking about, but we refer to them as products because the boundary around steel, for instance, as defined against Robinson, when we talked about this, is rolled steel. So it's been processed up to a point, so it's not a commodity per se, it's sort of a early in the chain product. I don't know if that answers that. In terms of, like, I have a complex piece of electronics, and I know precisely, I can roll up all that's the ideal that are unlikely to ever reach, in my opinion.
All right, thank you.
I think of something like milk where you don't know what cow that milk came from, right? So it could come from various farms. So up that supply chain, I think things get very, very tricky. Yes?
This is a quick question for CARB. In the emissions, and money is running out. In the emissions that you look at, there's a target, it sounds like, for low GWP, a real emphasis on that. Is there an emphasis on toxicity? And what I mean by that is like accounting for emissions from refrigerator machines, like HFOs, and they're low GWP, but then when they leak out, they're trying to run out of gases, which is really hard to wonder what's CARB's stance on that.
Yeah, I'm unfortunately not the right person to ask about that. I know we do have a team that works on those high GWP gases as well as methane, but But as far as the toxicity, I think that would be probably covered through our Department of Toxics. So
Further questions? Before we go to Kelly,
Anybody else?
anybody else?
Yes, I will.
Kelly?
All right, just a question on cap and trade, David. So, you know, when I watched it, the price for carbon, a metric ton used to be around $20 per metric ton. It's drifting up to $40. Do you have any projections? You know, I know you don't set a price, right? But by varying the allowances for where this is going?
Oh, that's a great question. I mean, because I'm definitely not allowed to project what the price of carbon is.
Well, that's why I asked.
But it has been very interesting because it has been around the floor price for the first 5 to 8 years, and then now it's increased. However, we do have several speed bumps in the program, price containment reserves. We also allow for offset credits through forestry and some other programs. And then we do have a price ceiling that we have all types of mechanisms. If the prices ever got that high, we could sell additional units that then CARB would have to work with to try to find where those reductions are actually taking place. So we do have some higher price sides of that should keep it constrained, so it's not a full just market system. But yeah, it's been very interesting because the price has, in the last auction, went down significantly after it peaked at that 40.
Thank you.
Any other questions? Well, I'll ask on the SAM and Vedant with load shifting. What industrial operations, in your view, in the work, do you see as being candidates for load shifting? Or maybe the flip, what operations are hands-off, no load shifting, not happening here?
I would say process heating.
Is hands-on or hands-off?
Hands-on. And electrochemical processes, basically anything that is used for ammonia production. Those probably are the ones that we think of as low-hanging fruits for electrification.
I would say it depends if you could categorize it into loads that you can manually ship. So maybe we schedule a ship onto a facility manager or DER devices, and then management systems that we, let's say, based on price signals, if you're lighting, pre-cool, preheat, use purchase storage. So the processes that you could potentially automate using DERs, especially ones that you can automate with DERs that are not integral to facilities operations in terms of the shifting manually scheduled, those would be, I'd say, low-hanging fruits for shifting. And going forward, you can also reschedule shifts based on what your carbon price signal tells you if you have rating carbon.
Thank you. Well, I think we're at, unless there's any other questions, I think we filled one more, but I'm also happy to give you guys a couple more minutes. All right, well, please join us for the closing plenary. I think it's going to be in the big room. That would make the most sense. I think we have a couple minutes, so refresh yourselves and then make your way over there. But thank you very much.